second derivative test. Okay, given the graph of the cubic function and the relative maximum point here at the 0, 2 and the relative minimum point here at the 2, 0, yeah. Okay, first the relative maximum point at the 0, 2, yeah. So the first interval between negative infinity and x equal to the 0. The first value of x here equal to the 0. Okay, between negative infinity and x equal to 0, and the shape of tangent here increase, and here you put the positive sign, yeah. So the first derivative here greater than 0, positive, and then after x equal to 0, the gradient of tangent here decrease. So the sign of the first derivative here negative, 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 and negative. And after 2 here, the graph here increase to the positive infinity. So here you put the positive sign, yeah. Okay, and using the first derivative test, the relative maximum here exists at the 0, 2 when the first derivative here equal to 0. So here the relative maximum at the 0, 2, yeah. And the second method, this one the first method, using the first derivative test, okay. And B, the second method, using the second derivative test. Using the second derivative test, the sign of the second derivative here less than 0, or the sign here negative, okay. And when the sign of the second derivative here negative, so conclusion you the relative maximum here exists. Okay, second graphs. Graphs here, the relative maximum at the point A. Okay, this one the relative maximum point at the 1, 1, and the relative minimum point here at the point B. Okay. Okay, first you check the sign of the first derivative. So the tension here decrease between negative infinity and negative 1. So here you put the negative sign, negative, 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 and after point B here, the tension increase to the positive infinity. So here you put the positive sign, and after 1, the gradient of tension decrease to the positive infinity. Yeah. So using the first method, the relative minimum point here exists when the first derivative here equal to the 0. Yeah. So this one the relative minimum point. Okay, and B, using the second derivative test, SDT, you substitute the value of x into the second derivative, and then the sign of the second derivative here greater than 0, or here the positive sign. Okay, and conclusion you graph here with the relative minimum point. Okay. Okay, question 5, find the coordinates of the stationary point using the second derivative test and determines the nature of the point A. Y here equals to the x cubed minus 6x squared plus 9x plus 1. Okay, given the cubic function, y here equals to the x cubed minus 6x squared plus 9x plus 1. Yeah. First here you find the first derivative of the cubic function. Differentiate y with respect to the x. So first derivative dy over dx here equals to the 3x squared minus 12x plus 9. And then you let the first derivative here equal to 0. So stationary point here exists when the first derivative equal to the 0. Okay, first derivative equal to 0, 3x squared minus 12x plus 9 equal to 0, and you factorize the quadratic function. First factor here 3x minus 9 times x minus 1 and equal to 0, and you find the value of x. The first value of x here equals 3 and x here equals to the 1 here. Okay, and step 2, you find the value of y. So first value of x here equals to 3, and you substitute into the cubic function here, and the value of y here equals to 1, and the first xy here at the 3, 1, the first point, and the second point x here equals to 1, and you substitute into the function, and the y here equals to 5, and the second point here at the 1, 5. Okay, using the second derivative test, determines the relative maximum and the relative minimum point. So the first value of x here equals to 3, and you find the second derivative. Second derivative here equals to the 6x minus 12. So you substitute 3 here into the second derivative, and the second derivative here equals to the 6, and the value here greater than 0, or the sign of the second derivative here positive. Yeah. Okay, and conclusion, when the sign of the second derivative here positive, so 3, 1 here the relative minimum point. Yeah. Okay, and the second point, when x here equals to 1, and you substitute into the second derivative, 6 minus 12, and answer here equals to the negative 6, or here less than 0, and the sign of the second derivative here negative. Yeah. And conclusion you here, when the sign of the second derivative negative, and the 0.15 is the relative maximum point. Yeah. So here negative sign, and conclusion you the relative maximum point. Okay. The basic concept of the second derivative test, when the sign of the second derivative here positive, so conclusion you the relative minimum point, and when the sign here negative, conclusion you here the relative maximum point. Okay, inflection point. Okay, so inflection point here defined when the graphs when the second derivative equal to 0. Okay. Okay, given the graphs of the cubic function, and here you put the dot line at the x equals to 1. Okay. Okay, first domain of the cubic function. Domain of the cubic function is all the real numbers, negative to the positive infinity. Yeah. So first interval between negative infinity and x equals to 1. Okay, you check the concavity of the function. So graph here concave up between negative infinity and 1. Yeah, and the sign of the second derivative here greater than 0. Okay, greater than 0, or here you put the positive sign. Okay, and the second intervals between 1 to the positive infinity. Okay, and the graph here concave downwards, and the second derivative here less than 0, and the sign here you put the negative sign. Yeah. Okay. From the left of the function, graph here concave up, you put the CU, and after 1 here, graph here concave downwards, this one you put the CD. Yeah. So conclusion U here, inflection point exists when the concavity difference on the both side of the point. Yeah. From the left here, graph concave up, and after 1 here, graph concave downwards. Okay, second graph, this one the graph of the cubic function when the fx here equals to the x cube. Yeah, you check the concavity of the function. So maybe the value of x here equals to the 4. Okay, and this one from the left of the function, you check the interval negative infinity 4, and the second interval here 4 to the positive infinity. Yeah. Okay, and here you check the concavity of the function from the left of the function between negative infinity 4, graph here concave downwards, CD. Okay, and the sign of the second derivative here less than 0, or here you put the negative sign. Okay, and then after 4 to the positive infinity, graph here concave upwards, CU, and the sign of the second derivative here greater than 0, and here you put the positive sign. Yeah, and the inflection point here exists at the 4 when the second derivative change sign. Okay, first interval here second derivative negative, and after 4 second derivative here change to the positive sign. Okay, here example of the quadratic function. Okay, so you check the inflection point and concavity of the function. first here, from the left of the function, you put this one, the first interval. Okay, so here the first interval, and here second interval, and here third intervals. Okay, so first interval here, between maybe the value of x here equals to the -1, and the second value of x here, x equals to the +1. Yeah, the first interval between -infinity and x equals to the -1. Graph here concave up, so you put here cu, and then between -1, 1, graph here concave downward, cd, and here the inflection point. Yeah, so you label the inflection point here as is, POI, the first inflection point. Okay, and the second, after 1 to the positive infinity, graph here concave up, cu. Okay, and the inflection point here as is, here. Okay, and relation between the sign of the second derivative and concavity of the function. Okay, first you check the sign of the second derivative. This one, number 1. The sign of the second derivative here less than 0, or here negative sign. Yeah, so graph here concave down, and the conclusion you the relative maximum point here exists. Yeah, so you draw the smile face here. Okay, number 2, the second derivative here greater than 0, or the sign of the second derivative here positive, and graph here concave up, cu, and then conclusion you here the relative minimum point exists. Okay, and you draw the smile face. Okay, question 6. You state the inflection point based on the given graphs. First, you state the relative maximum and the relative minimum point. So the relative maximum, okay, the relative maximum point here exists at the -3, 2. Okay, and second point here at the 2, 1. And the relative minimum point exists here at the -1, -3. Okay, and the second relative minimum at the 4, -1. Okay, settle. So graph here 2 relative maximum and 2 relative minimum point. Okay, and number 3, you state the inflection point, POI, point of inflection. Okay, and first you check the concavity of the function. First here from the left of the function, maybe you put here the first point here first, and the second point here. Okay, first the value of x, this one maybe first point, at the negative 2, negative 1/2, yeah. And the second point here maybe at the 1/2, negative 1/2. Okay. Okay, so from the left of the function, negative infinity and x equals to the negative 2. Okay. So graph here concave downwards CD. And after negative 2 here, negative 2 and positive 1/2, graph here concave up CU. Okay, and conclusion U here, inflection point here exists. Okay, so first inflection point at the negative 2, negative 1/2, and then after 1/2, and graph here concave downward CD. This one you put the CD. Okay, and the inflection point here exists. Okay, you check the concavity of the function from the left, CD, CU, concave down, concave up. So between here, inflection point exists. And then between negative 2 and 1/2, graph here concave up. After 1/2, graph here concave downwards. Okay, so the second inflection point at the 1/2, negative 1/2. Okay, and the third point maybe here at the x equals to 3 and y here equal to 0. Yeah, and you check the concavity of the function. After x equals 3, so graph here concave upward CU. Okay, and the conclusion you here, the inflection point here exists at the 3, 0. Yeah. Okay. Okay. So graph here, relative maximum 2 point, relatives minimum negative 1, negative 3, 4, negative 1, and 3 inflection point. Okay, question B, your exercise.